Hello everyone, I am Tian Peizo, a PhD candidate from Tongji University. Today, I am going to present our recent work on test time adaptation, HGL, hierarchical geometry learning for test time adaptation in 3D point cloud segmentation. As we know, deep neural networks usually fail to generalize well to outside of distribution data. To address this challenge, several appealing solutions have been developed, including domain generalization and domain adaptation. However, as shown on the left side of the figure below, DG primarily operates during the training phase and cannot fully utilize test data from application scenarios. DA typically necessitates access to both labeled source data and test data concurrently, constituting offline learning, and can be hindered by privacy concerns or legal constraints. In many practical scenarios, DNNs require continual and adaptive updating in an online fashion to remain effective. Hence, we focus on an extreme case in domain adaptation, test time adaptation, in which model adaptation is performed by learning from the unlabeled test target data during inference time. Currently, most TTA approaches are proposed for 2D image data, as shown in the figure below. The direct application of these techniques onto 3D point cloud data is not practical and yields negligible results. More recently, GIPSO, designed specifically for TTA in 3D point cloud segmentation, leverages geometric and temporal information to mitigate the domain shift. Nevertheless, GIPSO lacks a deep exploration of the geometric characteristics of point clouds, resulting in suboptimal result. In this work, we target TTA 3D seg from the viewpoint of parsing continuous unstructured point cloud streams into local, point level, global, object level, and temporal, frame level, hierarchical structures for accurate and robust self-supervised learning. Technically, HGL comprises three complementary modules. First, local geometry learning generates pseudolabels by employing KNN information aggregation. Then, global geometry fine-tuning builds prototypes for pseudolabel fine-tuning with increasing target data. Building upon the first two, temporal geometry regularization is introduced to mitigate negative transfer. As a promising technique in unsupervised learning, pseudolabeling has been widely employed. Existing methods typically generate pseudolabels directly based on single-point prediction, neglecting the local geometry structure, which results in suboptimal results. To tackle this, as shown in figure, we propose the Local Geometric Learning (LGL) module. The Local Geometry Learning module is based on the local KNN clustering strategy, which includes aggregating predictions for each point from its nearest neighbors and calculating confidence by both geometric purity and prediction certainty. The prediction certainty is the anti-entropy of each point prediction. Besides, the geometric purity represents the purity score of surrounding points, obtained by calculating anti-entropy based on the predictions of neighboring points. With geometric purity and prediction certainty, we obtain the final function of confidence score as S equals CA. Then we exclusively select lambda th percentile of S for each class as selected local geometric pseudolabel. Although the pseudolabels have been enhanced with local geometry through LGL, there are some limitations. Firstly, the generated pseudolabels are still noisy due to domain shift and cannot benefit from the continuously increasing target domain data. Secondly, the selected local geometric pseudolabels are chosen by lambda. It is challenging to ensure a good balance between accuracy and generalization in the selected samples. Based on selected local geometric pseudolabels, we further introduce a global geometry fine-tuning module, in which we build prototypes for each class object on the target model and employ them as a new classifier to obtain global geometric pseudolabels. By incorporating local and global geometric pseudolabels, we could obtain robust and generalized local global geometric pseudolabels. Lastly, we introduce a temporal geometry regularization module to constrain the consistency of the embedding feature of geometrically corresponding points between the current point cloud and the previous. In contrast to forcing regularization at all points, we align low confidence to high confidence features to avoid degradation of high confidence features. We have evaluated our HGL framework on extensive tasks, including 2 virtual datasets, SimlyDAR and Synth4D, and 2 real-world datasets, Semantic Kitty and New Scenes. Here are the results on synthetic to real setting. We can see that HGL shows remarkable performance, surpassing existing methods by a significant margin. We also conduct extensive experiments across other adaptation scenarios, including real-to-real, continual learning, and adverse weather. We also conduct experiments regarding efficiency. HGL consistently performs well in all settings and reduces the adaptation time by 80%. Besides, it is important to note that HGL is a general framework. The specific implementations within each module are not firmly fixed and can be updated to incorporate advancements in the field. Moreover, integrating HGL into GIPSO to build a thorough local global temporal structure results in notable improvements. To examine the contribution of different components within HGL, we have conducted extensive ablation studies. Results show that both all modules are effective. Additional hyperparameter analysis show that our HGL is not sensitive to hyperparameter selection. We also conducted numerous additional meaningful experiments, and further details can be found in our paper. Here are qualitative results of our pseudolabel and segmentation result. It is clear to find that LGL can accurately select pseudolabels, while GGF can generalize them to a wider range of points. Here are some visual comparison between HGL, GIPSO, and the source model on SimlyDAR to Semantic Kitty, which show that our GLC are generally superior to GIPSO. Here are more visual comparison in different datasets. In summary, in this work, we propose a hierarchical geometry learning (HGL) framework for TTA in 3D point cloud segmentation. And extensive experiments have demonstrated the effectiveness of our method.